So I'm going to talk today about robots working with people. I'm going to talk about a bunch of things, but I do want to acknowledge, in particular, the 27 PhD students, but also my postdocs. But these are the 27 PhDs. Their numbers are 1 to 9, so on, down to 27. So I won't acknowledge individually their work at each point, but they have been very critical in the things I'm going to talk about, along with postdocs and master's and bachelor students. So I'm going to talk about perspectives on our robotic future, but from the point of an academic refugee, which is what I consider myself. And I'm going to try and tell you a bunch of things today, variously about the difference between academia and industry from a couple of different perspectives in 2 doses, and then talk about where robots may be leading us in the future. And most of the pieces for lots of interesting stuff have already happened in labs, and I'm going to give some demonstrations or some movie clips from some of the robots that we developed, my students and I developed here at the lab over the years. And in fact, once I joined the faculty here in 1984, I started building mobile robots for many years, and these are some of the mobile robots my students and I built. I never think of it as an ant exactly, Victor, but okay. 6 legs, certainly. Various 6-legged robots, various robots of various sizes, humanoid robots, and we'll come back to humanoid robots. We'll come back to Kismet in particular. Kismet's on your left, Cynthia Brazil, who's on the faculty of the Media Lab, is on your right, and some of the more recent humanoid robots, and we'll talk about them towards the end. I had, along the way, I was always starting companies, and I'd started a bunch of companies. But then, around 1988, I was in particular working with NASA and looking at NASA's plans to send a rover to Mars. And they were talking about a $12 billion mission to Mars to send a 1,000-kilogram rover. And that didn't seem very likely that there was going to be budget for that. And so I wrote this paper, along with Anita Flynn, one of my students, called Fast, Cheap, and Out of Control, A Robot Invasion of the Solar System, which we published in the Journal of the British Interplanetary Society. Now, you may not know that journal exists, but that's where the first communication satellites were the idea of them was published. And I couldn't resist publishing a journal with that name. And the idea was, well, instead of sending a 1,000-kilogram rover, why not send 100 1-kilogram rovers? If they could do the same work, it would be quicker to develop 1-kilogram rovers. It would be cheaper to send only 100 kilograms worth of stuff. And if you had 100 of them, well, if you got one rover and it costs $12 billion to get it to Mars, you're not going to let it do anything dangerous. But if you got 100 of them and they operate autonomously and you don't need to control them from Earth, maybe they can go do interesting stuff, because you lose a few, you've still got the mission. And Colin Angle, who was my bachelor student at the time, went out to JPL and built a little prototype weighing half a kilogram in 1989, and that got people sort of interested because it could do the same as the big robot. Oh, I got to tell you one thing. You can tell this is 1,000 kilograms. You can tell it's a NASA robot because of the gold foil covering stuff. That's important. And so then there was a very small team on a very low budget stayed on using our system and built a series of robots called Rocky for their rocker bogey mechanism, and then the second one was called Rocky 2, and the third one was called Rocky 3. You can tell this is a NASA robot because of the gold foil around the Sony camera there. You can also tell the low budget because the body of the robot is a Macintosh case, for those of you old enough to remember it. But NASA was really, really slow, so we got frustrated with them. You know, we got to do this, we got to do this. So, you know, Colin Angle, who's an undergrad, and Helen Grainer, both of them were master's students by this time, and I decided, well, maybe we could do it ourselves. You know, why do we need NASA to send something to Mars? We can do that. So we started a new company called IS Robotics, which eventually became iRobot. And our plan was to send small robots to the Moon and Mars, cheap planetary exploration. This was our first business model. This is a lesson here about business models. And the idea was to send multiple of these rovers, and, you know, we were thinking, well, you know, we could have Coca-Cola decals on the side of them, and we could sell advertising space. That would pay. We thought we needed $22 million to go to the moon. We were going to have a Saturday morning cartoon series, toy, co-release, everything. We had a business plan that went out 20 years. because everyone requires a business plan that goes out 20 years on how we're going to do it. We tried to get a launch. We had a problem finding a launch. We talked to 6 private launch companies. None of them had had a successful launch at the time. Only one of them has since. It's another business plan story. But eventually, we talked to the Ballistic Missile Defense Organization, which many of you are far too young to remember. But they had been in existence during the 80s from Ronald Reagan to shoot down ballistic missiles that the Soviet Union would send up. And this vehicle here is called a Brilliant Pebble. It was a kinetic kill vehicle. It was designed to sit in orbit, and when the USSR sent up a missile, it was just going to go shoot down and collide with it and knock it out of the sky. But by 1992, the Soviet Union didn't exist anymore. BMD, Ballistic Missile Defense Organization, Star Wars, didn't have an opponent, so they were eager to talk to us. Any business was good business. And so we added legs to one of these Brilliant Pebbles. We built a little tiny rover, and this was just the Earth version of it. And we put it in, we took out the instrument pod from the Brilliant Pebble, put the rover in there, didn't talk to it for 4 days. That was like getting into lunar orbit. There was enough delta V on the Brilliant Pebble to land on the surface of the moon. And so this was our test out at the old Saturn V test building in October of 1993. And I would like the sound up for this one if we can. So on the bottom right-hand corner there, you see 14, the Brilliant Pebble 13, with the robot in it. 12, and 11, 10. We're doing a soft landing in Earth gravity. 7, the idea was 6, to send it with the Clementine 5, mission, 4, which later did fly 3, to the moon. 2, deploy 0, down and land next to the Apollo 15 lander to do some metallurgy. +4, +5, +6. So we're doing soft landing here. +8, as it lands, it wakes up the robot. The robot is in a passive pod, which is gravity loaded, so it will right itself no matter how it falls on rocks. And then you'll see the rear leg on the right there of the robot unlocking itself from, let me out, let me out. It's woken up for the first time in 4 days. And now it's going to stand up and go off and do its metallurgy on the Apollo 15 lander. So we were going to go to the moon. Except Dan Golden at NASA wasn't pleased by this because NASA was in charge of civilian space research, not Star Wars. So he said, oh, by the way, I've got this little Rocky project out at JPL. And by now they're up to Rocky 6, which was the one that Colin and I had started. And he said, we're going to go to the Mars in 1997 anyway. It's only going to cost $25 million to do a last-minute add-on of the rover. So Sojourner ended up on the surface of Mars. It was the descendant of Colin's robot that he built in the summer of 1989. And we got, for the first 28 sols, we didn't get much time, but after sol 28, it was set running with subsumption or behavior-based architecture and went off exploring by itself, totally autonomously. So we did manage to get a robot to Mars indirectly. We didn't send it ourselves. But it was one of our 14 failed business models at iRobot before we got success. Persistence is an important thing. Some of these business ideas were better than others, but we spent a lot of time on each of them. But eventually we did manage to get robots into people's homes. And as Victor said, robots out into Afghanistan, Iraq. The center one there is diving into the ocean is a sea glider. We had them down in the Gulf over the last few months looking at where the oil is underwater. They can go for months at a time. And that was a lot of fun. Sort of taking ideas that we'd had in the lab at MIT and turning them into a real company. In fact, eventually, we did an IPO. This was in Times Square, the day of our IPO. And that was fun. The company was called iRobot. People remember in 2005 there was another iRobot event? There was this movie called iRobot. And after the fact, we sort of noticed some similarities. You know, there was sort of the elderly academic. Then there was a good-looking, beautiful scientist. And then there was a hard-charging young CEO. You remember how it worked? Before the opening credits, the academic is dead. By the end of the movie, the CEO is dead. Helen liked this movie a whole lot better than Colin and I did. Now I'm at Heartland Robotics, and we're trying to build robots to help the manufacturing industry in the US. And I'll talk about that a little bit, but not Heartland itself. But I want to talk about where robotics might be heading. And I'm going to use three methods. I'm going to talk about some worldwide trends and pulls, general technology exponentials, and some recent technical advances. And then I'll come back to the academia-industry split. So this is Europe in 1950. And those of you who have seen me give talks over the last few years, I'm sorry, I'm showing these slides again. So many of you have seen these. This is the population of Europe in 1950. It's a histogram with men on the left and women on the right in 5-year age intervals. So that's the age distribution. And you see the notch around 30 to 34 taken out by the Second World War, everyone getting killed there. But that's the shape of the population of Europe, 350 million in 1950. Here it is in 2000, and here it is in 2050. Now notice it went from 350 million to 450 million. It's going to go back to 400 million, but the snake swallowed something. And there's going to be a lot more older people than younger people. The ratio of older people to younger people is going up significantly. So everyone talks about Social Security, being an issue. How do we pay for Social Security? But it's worse than that. There's a second-order effect. The people on Social Security will be competing for services from less relative number of younger people. Productivity has to increase of the younger workers, even as we keep trying to, we will be pushing the retirement age higher, but productivity of younger workers will have to increase. That's going to pull all sorts of things, wanting productivity increases, especially in the physical world of doing physical stuff. There's not just information technology, there is physical stuff. This is Japan, same sort of data from 1950, more dramatic even. You might wonder why there are so many 90-year-old women in 2050. Well, that's because that's the 90-year-olds and the 100-year-olds. It turns out, if you want to live a long time, be born a Japanese woman. And even better, be born a Japanese woman in Okinawa. I missed the boat, but that's how to live a long time. But Japan already is suffering from the aging population. In the US, the red line is the percentage of population over 65, and you see we're just at the start of an enormous increase in percentage of population. The baby boomers are getting gray, and we're going to be such pains to younger people, wanting to, can you buy my groceries for me? Can you do this? Can you, bathe me? I think there's going to be a real pull for productivity increases. That's just the same, the US data in the same sort of format as before. So there's going to be a lot of pulls. Working Americans will need to become more productive in all sectors. Now, the last 3 or 4 years, I've been worrying about manufacturing in particular. U.S. manufacturing sort of has a bad rap, that we've lost it all. In fact, as recently as 2008, total value add in U.S. manufacturing was bigger than total value add in China, although it's about even, they're $2 trillion, each of them. But certainly, productivity in U.S. manufacturing has increased dramatically over the last 60 years at a roughly 3.7% for 60 years. That's a pretty long run of productivity increase. But it's done it with mostly flat employment. And it's done it because U.S. manufacturing has shifted from necessities to higher value-add things, high ticket items for defense, for high-performance systems, and left to China all the low value-add stuff, the stuff you buy at Walmart. So that's how U.S. productivity in manufacturing has gone, but it's led to a rather serious problem for us in terms of balance of payments. And U.S. manufacturing since World War II has been outsourced continuously. At first it was outsourced to Japan, and many of us are old enough to remember that in the 60s we started seeing made in Japan labels that we hadn't seen before, with electronics goods in particular. But then as the standard of living went up again in Japan after the Second World War, then it moved to Korea, the manufacturing outsource. Then the standard of living went up there, it moved to Taiwan. Then in search of low labor costs, it moved to mainland China, and Shenzhen, the south of China. Since about 1998, low-value stuff like plush in toys, sewing. You wouldn't sew in China anymore. You do sewing in Vietnam. And now higher-value stuff, electronics, is starting to move to Vietnam. But pretty soon you run out of low-labor places because coming in from the left, from Indonesia, Malaysia, and Thailand, we've already had the increase in standard of living, and so there isn't the low-cost labor there anymore to exploit. So the West has been off exploiting low-cost labor, and we're sort of running out of places to go for it. Here's the labor cost in some of the countries I talked about, and you see how Germany's the highest hourly labor cost in manufacturing, France, then United States, then Japan, then South Korea, then Taiwan, and then Mexico and China. So you see that where we've been tracing low wages, the wages keep coming up, everyone's standard of living raises. So in these low-cost goods, here's just Walmart. Back in 1985, by the way, the import-export imbalance due to manufacturing between China and the U.S. was $5 million a year. It's now $321 billion. That's a big increase in 25 years. So tremendous strategic pressure on the U.S. dollar from low-cost manufacturing happening in China, in particular, what I call Walmart class manufacturing. The stuff that we buy cheaply is made in China for us. And in low-end manufacturing, young Chinese workers sit next to conveyor belts. They pick things up, they do a little manual job, and they put them back. And these particular low-cost labor workers are building robots. They're building Roombas for iRobot. And this is the raw materials they build production lines out of, stools and tables and conveyor belts. And this is where the stuff that you buy from Walmart gets made. Well, what if we are, as China's standard of living goes up, as labor costs go up in China, as more domestic demand comes in, what if we can't afford to do low-cost manufacturing in China anymore? And there's been a great example this last year with the iPhone. Foxconn makes the iPhone, and you may have heard the stories earlier this year that with a lot of suicides in Foxconn, the labor rates went up between 50 and 100% at Foxconn factories in 1 year. There are other things which make manufacturing difficult in China. In 2008, when do people remember 2008? It's a long time ago, summer of 2008. Anyone remember what the price of oil was, summer of 2008? What? Sorry? Barrel? Yeah, it was well over $100 a barrel. Fuel surcharges for bringing stuff from China got slapped on, and every company that was importing stuff for retail lost all their margins in fuel surcharge costs. Fuel prices have gone down, but I'm guessing they're going to go up again at some point. That's my prediction. You heard it here. Oil price will go up again. So there's lots of reasons that we may not be able to sustain manufacturing in China. So can we use robots? Why don't we use, we use robots for automobiles. Why don't we use them for, saucepans in Walmart? World's first industrial robot, the Unimate, developed by Joe Engelberger, who's still alive, first installed in a GM factory in 1961. For a little while, I could make a joke. The people remember GM, but they just did their IPO, so I guess they're back. So a GM factory in New Jersey, first industrial robot. Unimate, it was called a Unimation, the company. It was later bought by Westinghouse and then sold to Kawasaki. But there were technology limitations back in 1961. The robots had no computers, no sensors, and they just did the same motions again and again repetitively with hydraulics. So the robots would just do the same thing again and again and hope that the right things were there to pick up and move or weld or whatever. So today's manufacturing robots are actually very similar. They do have microprocessors in them, but they emulate 12-volt ladder logic. They're sort of emulating the way they were programmed and interfaced with back in 1961. The revolution of PCs and cheap sensors hasn't really come to them. And so they do the same thing again and again, without sensing, and as a result, they're incredibly dangerous. You don't want to be near them. They'll kill you, not because they're mad at you, not because, you're going to switch them off, but just because, everyone asked me about that. Just because they won't see you and they'll hit you. And because there's no sensing involved in them, the integration cost to put them in the production line is about 5 or 10 times the capital cost of the robot. They're a really old, slow, dull technology. Now, I think Victor and maybe no one else here remembers mainframes. Back in the old times, there were mainframes. And you didn't get to touch a mainframe. Ordinary people didn't touch computers. It's hard to believe, but ordinary people didn't touch them. Maybe you would punch cards or write on your code out on a coding form, and then there'd be professionals who'd punch the cards, load the cards. They were called computer operators, load the magnetic tapes, and you'd eventually get your output. That was if you were at a university. If you're in business, you'd just get a fan-fold output of the sales reports, once a week, and you'd look through it. If you didn't like the numbers you were getting and you were in charge, you'd talk to a systems analyst, and the systems analyst would design a change in procedure, and then a programmer would do it, and it would go to the punch card machines, et cetera, et cetera. You didn't have direct control over information. But now, ordinary people can touch computers. It first came with PCs around 1980, 81, and then just a wealth of things came out of that. Completely transformed the experience of interacting with computers. By the way, ordinary people became programmers too. They didn't think of themselves as programmers, but with spreadsheets, they were doing simple programming operations. Now, right now, one of the reasons, by the way, you couldn't let ordinary people touch computers is because ordinary people smoked, and smoke got in the disk drives and made them crash, the smoke particles. Today, ordinary people can't touch robots because they're dangerous, and they're really hard to program and get to do anything. So the question is, what if ordinary people could touch robots? Could we have that transformation of society that we went from mainframes to PCs, if we went from these dangerous robots to sort of touchy-feely robots that ordinary people could program? Would that change our society as much? And I claim it would. And I can also claim that now ordinary people can touch robots. Up on the top left there is Intuitive Surgical's surgical system, and the surgeon is over on the left controlling the robot, laparoscopically operating inside the person. And this is a very common way of doing operations. You might argue, well, a surgeon, is that a surgeon, an ordinary person? Surgeons have a different view of that joke that none of you got. Anyway, but soldiers deal with robots. People in homes deal with robots. And making the robots just get to the point that ordinary people could touch them has led to a tremendous uptake in this last decade. In June of 2002, there were no ground robots in the US military. As of January of this year, there were more than 7,000. In June of 2002, there were no robots in people's homes in the US. As of January of this year, there were more than 5 million. So we see some pretty tremendous uptakes once you let ordinary people touch the technology and buy it themselves. And why have things taken off? Well, computation and sensors have gotten exponentially cheaper for 50 years, and putting computation and sensors into robots made a big difference. Research in computer vision and simultaneous localization and mapping, SLAM, and there's a whole bunch of people I saw in the audience today who've contributed to this, have made major strides in the last 10 years, partially due to so much more computation being available. But robots can now see certain things and know where they are, and we couldn't do that very well just a few years ago. And for certain tasks, robots have passed the usability threshold where an ordinary person can use them and interact with them. Not manufacturing yet, but cleaning the house certainly. So there's a few things going on there, and I just want to make a little sidetrack and talk about IT exponentials, because that's really important. Information technology exponentials. We sort of think about what we're doing, and we know there are exponentials going on, but we sometimes don't quite realize how that keeps changing the game again and again and again on us. And I just love looking at this paper from Gordon Moore from 1965, where he first talked about exponential growth in the number of components on a chip. It's a 10-page little article in a sort of throwaway magazine. And he still is, such a smart guy. This is his first two paragraphs where he predicted, this is in 1965, that integrated circuits would lead to home computers, automatic controls for automobiles. If anyone here has a 50-year-old automobile, you'll know how little electronics there were in them back then. And personal portable communications equipment. He predicted the cell phone. He didn't know what form it would take, but this was back in 1965, when, by the way, there was not a single computer using an integrated circuit. I'll get back to that in a minute. There was a cartoon with this article. And a few years ago, I asked Gordon whether it had anything to do with the cartoon, and he said it was a total surprise when he opened the magazine and saw this cartoon. But there you see cosmetics on the right being sold right next to someone selling handy home computers. My guess is the cartoonist was sort of making fun of the article. You know, yeah, we're going to have cheap home computers, sure. But the laugh is on the cartoonist, because that's what happened. And this is the best part. This is his data. This is the whole data that he had. 4 data points. 1 null data point in 1959, and 4 data points on the number of components on a chip, spread between 1962 and 1965. It's a log scale on the left, and he just drew a straight line, interpolated it. But he only went out 10 years, and he said he didn't dare go longer than that. You know, it couldn't last longer than 10 years. But that was predicting 2 to the 16th, 65,000 components on a chip by 1975. And that's what happened, of course, and it's continued to happen. Well, why did that happen? Why does it continue to happen? What defines an exponential? Well, the rate of change in the amount of stuff is proportional to the current amount of stuff you have. That makes an exponential, right? So is this an explanation for why computer power keeps rising exponentially? Is it because once you've got a certain power computer, you can design the next one and the next one? Well, maybe, except it wasn't in play in 1965 because, as I said, there was no computers with integrated circuits. In fact, the first computer with an integrated circuit was the Block 1 processor to land the lunar module on the moon. It never flew. It was developed just over the road at Draper Lab. By the time they flew the first mission to land, it was the Block 2. In the Block 1, the integrated circuits had 1 gate per integrated circuit. It was a big radical shift to go to 2 gates per integrated circuit for the flight hardware. So this was before that. This exponential started. It wasn't in play in 1965. In fact, I think there's 3 ways exponentials happen. One is the rate of improvement is proportional to the current level of adoption. And we see, you know, that's sort of related to Metcalfe's law about networking effects of things. You know, once there are a few people in the network, then there are more, and then there are more, et cetera. But sometimes it's the existence of the law tells everyone what to aim for. And if you went into, memory chip companies in the Valley in the 70s and 80s, they all had how many bits per chip you needed in what year. The engineers had to walk past that every morning and see what was expected of them for the next 10 years. They knew what they had to do. The law told them what they had to do. It told them when they had to develop a new plant with a new process, when they had to, cut the size of the traces of the wires in the silicon, etc. And the third one is that someone else is driving an exponential, and you get to hop on it for free. And this is the nirvana of robotics. Robotics isn't driving many exponentials yet, but there's all these other exponentials going, mostly due to these devices, that robotics just gets to hop on and ride for free in terms of processor power, sensors, cameras, etc., and both price and performance. And these places, these exponentials help robotics in all sorts of things involving making better robots. I just want to step back for one second, though. Why is it that information technology has exponentials? What is so special about information tech? Why can you put double the number of components on a chip all the time? That's really because information technology has a special relationship to physics. And information technology is based on a 1-bit abstraction for a bulk physical property. Now, that's not true for, say, a robot arm. If a robot arm can pick up 10 kilograms, you can't half the size of the robot arm and still pick up 10 kilograms. It will start sagging. But a bit is a bit is a bit. So if you have a pile of red sand versus green sand, you can tell which one's red and which one's green. Take away half the sand, you still have a pile of red sand or a pile of green sand, and you can tell whether it's red or green. Take away another half, take away another half. That's why information technology can have exponentials, because that physical bulk can be reduced while maintaining that abstraction. Some of you may have seen, people complaining about Microsoft saying, well, if Microsoft was, it was Microsoft complaining about cars or something. How'd it go? Now I feel like George Bush. I shouldn't add a new story in the middle of a talk without thinking about it. People said if cars had only gone like information technology, we'd better get from here to San Francisco on half a tank of gas at 10,000 miles an hour. But we can't do that with physical stuff, because the abstraction between the physicality and what you're trying to get it to do is unbreakable, whereas for information technology it is breakable. So we've got exponential technologies all over the place in information technology, and those exponentials in the direct technology beget other technologies. And that's happened to robotics in particular. Exponentials have impacted robotics. When I first came to Stanford, I came in 1977, I worked as a junior graduate student with Hans Moravec, a senior graduate student, and this was his robot. Every midnight, when everyone else had gone home, we'd set the robot up, connect it to the mainframe. This is from a 16-millimeter camera. The flashes are when the film was stopped. And at each stop of the robot there, you see the camera sliding from side to side. That's because it was a $50,000 camera. We couldn't afford two cameras to get stereo. And then it's 15 minutes of computation on the mainframe before deciding to move about a meter forward. And so the sun would come up around 6 a.m. People would start to show up at the lab. And if things had gone well, the robot would have gone 20 meters in 6 hours across this room. By the way, that camera was $50,000. About a year ago, I bought retail a web camera for $2.99. Now, it was a shitty camera for $2.99, but it was way better than this $50,000 camera from 1977. Everything would have been easier with that. It even came with a USB cable included for that $2.99. But that sort of shows you how exponentials, in the web change things for robotics in terms of, what sort of things you can get. And so that was 1979, 20 meters in 6 hours. In 1992, up in the AI lab, Ian Horswell, one of my students, had his robot Polly give tours of the lab. It would go for about 6 hours, 2,000 meters in a 6 hour period. And then in 2005, Stanley, the robot from Stanford, from Sebastian Thrun, went in the DARPA Grand Challenge, went 200 kilometers in the Mojave in 6 hours. So that's actually 13 orders of magnitude, 2 to the 13th improvement in 20 years. 26 years. So doubling in performance every 2 years for 26 years. So there's an exponential increase in performance of robots. And much of it is attributable to the exponentials in information technology. So robotics gets to ride on these other exponentials. The robots that we're going to want helping us, as Victor and I, not the rest of you, but as Victor and I get older, and we, we need help. We need services. The robots are going to help us. Are going to have to interact closely with us. But all the pieces, I think, are sort of around and have been. I'm going to use examples from my lab here at MIT with my students over the last few years, but lots of other people have worked on similar things. This is a robot of COG, a robot we built in the early 90s. That's Cynthia Brazil, who I mentioned is at the Media Lab now. And we were just, let's take a video of how safe it is to be with this robot. And Cynthia's there waving that eraser around, and the robot's reaching for it. And you can see its head moving around, its eyes saccading. In a second, she drops it drops it, and it looks where it dropped. But the two of them were taking turns playing with this eraser. And we went back and we looked at our development plan, and we didn't have any turn-taking. We were over in that red dotted line. We didn't have any turn-taking planned for years out yet. It was many PhD theses away. But there was turn-taking happening between Cynthia and the robot. How could that be? It wasn't that the robot had got unexpectedly smart. What it was that Cynthia was picking up on the dynamics of what the robot could do and leading it and playing a game with it. And she was the one doing the interaction. But to an external observer, you couldn't tell which was which. That made us start to look at a lot of developmental literature, and we found this is a well-known thing that happens in child development. Mothers always think, even before you're in an undergraduate, mothers think you're smarter than you are. And they keep treating you as though you're smarter than you are and leading you in development by playing things with you in ways that you don't actually quite know how to do yet, but your mother thinks you do. She starts playing with you, and that leads the development. So we started putting that in our robots and finding ways to get people to interact with the robots, to lead them in. Here's a thing that really helped, and this was a surprise to us. Here, the robot eyes saccade somewhere, and then the head follows with the robot's eyes locked on. When the robot started doing this, suddenly people started feeling like the robots were a little alive. And up in the lab, my graduate students started putting partitions so the robot couldn't see them when they were working at night. Not because they were worried about privacy, it was just because every time the robot did something like this, it would trigger some sort of social cue in them, and they'd feel they had to look up. It's like having, Silvio, sort of standing, looking over your shoulder and looking around at you all the time. And I'm trying to prove the theorem, and it's very hard. So, and the graduate students had built the robot. They knew what was going on inside it, not much, but they couldn't stop their own behavior from being triggered by this external sort of thing. And Sherry Turkle, who's here at MIT and had been very suspicious of information technology, came and visited the lab. And this is from a book she wrote soon after, that she, Cog, the robot, noticed me as soon as I entered the room, and I found myself competing with another visitor for its attention. In blue, my visit left me shaken, not by anything that Cog was able to accomplish, but by my own reaction to, she puts in quotes, him. For years, whenever I'd heard Rodney Brooks speak about his robotic creatures, I'd always been careful to mentally put quotation marks around the word. But now, with Cog, I'd found the quotation marks had disappeared. Despite myself, I had behaved as though in the presence of another being. And it turns out it's really easy to suck people in and get them to interact socially. Here's another little thing that if you put in, people feel the robot is alive. Here, the robot is looking at Christy's eyes. She looks at something. It determines her gaze direction visually and looks at what she's looking at. And by the way, if I was trying to explain to Victor how to do something, I was trying to explain to him how to use an iPhone because Victor doesn't know this. I would be looking down at the phone, and Victor's eyes would look at my eyes and look down, and so we follow gaze direction all the time. We do that. We use that cue. So we can get the robots to do that, and we can get the robots to follow what a person is saying pay attention to without the person having to be trained to make the robot pay attention to something. We just can use the cues that they're normally used to using with people. We put facial expressions on Kismet, which was Cynthia's robot, and looked at the way that people across cultures, use 4 basic ways of having contours in their speech in order to show approval, prohibition, attention, and comfort to babies. And cross-culturally, people use the same sorts of prosodic patterns to show those 4 messages to kids, independent of language. We worked with Victor's group and Jim Glass and looked at some prosody in people's voices. And this is 4 naive-ish sort of subjects. Oh, we need sound, sorry. Can we have the sound? It's Annie, for those of you who know Annie.
Bien sûr.
Being nice to the robot.
Nice
She's
robot.
praising the robot.
You're such a cute little robot. Tu fais so süß. Good job, Kismet.
This is one of the developers.
Very good, Kismet.
So in each case, the robot starts in the same state.
Look at my smile.
And then responds to praise appropriately. these are all driven by the human, and it's independent of language. Here, we asked the person to get the robot's attention and indicate when they had the robot's attention.
Kismet? Hey, Kismet. Ah, there we go.
Vite, vite.
I'll just let you see one more example in a second.
Ici.
Kismet, do you like the toys? Oh.
Now here, I don't know if Uname's here, we asked people to prohibit the robot.
No. No. You're not to do that. No. That's not appropriate. No. No.
So you don't want to mess with Uname. This is very common. She starts imitating the robot.
Where'd you put your body?
The robot hangs its head, she hangs her head. And sometimes the robot's just too weird. This is Annika, who worked with me for many years as an assistant.
It's like looking at me.
It's like looking at me. So I'm not going to show you. I've got some more of Kismet here. In the interest of time, I'm going to skip over that with naive subjects. But I want to show you other things with our robots. This is, it's hard to do figure ground separation. Well, if you've got a robot arm, oops, why did that not go? Oh, I pressed it one too many times. If you've got an arm, you can go and push something and segment it from the background by physically moving it around. Now you know what the object looks like and separate it from the background. So here, put the object down, the robot comes, isn't quite sure what's the background, what's the object, the robot pushes it, and then it's able to get a 2D view of it and learn that very quickly. And we'll look over its shoulder here at a screen, and we'll see how it's segmented out. What is the object, what is background, and learn that from interacting with the world. So not just being a passive learner, but an active learner interacting with the world. Here's Paul Fitzpatrick teaching, again using some of Jim Glass's system, teaching names of objects on a single demonstration, single shot learning.
Ball.
Now when he says car, it looks back at where the car was. It knows where the objects are. Its field of view. It knows the name of them. Some single shot learning, much as children can do. And in fact, for those of you who are interested, Paul Fitzpatrick went on to do a classical experiment on language or word acquisition from Tomasello with the robot. And I'm not going to show this here. Teaching it a whole bunch of words over many hours, teaching it what find meant, what yes and no meant, how to do a search, how to build a search out of simpler pieces. So we can make our robots do some pretty interesting things in complex domains. I'm going to finish up in terms of robots with Aaron Edsinger's Domo. This is the robot Domo with its head moving around and figuring out, and this is a few years back now, figuring out not only its own head motion, subtracting that from the motion of Aaron as he moves around, and so being able to get motion detection even as the robot moves around in the world. And here is the robot looking at an object against a pretty cluttered background. Real world has lots of stuff in the background, and here's the robot moving a hammer around, predicting where it's going to be, and learning about the extent of the hammer just from holding it in its hand, feeling its center of mass, etc. Putting those things together, oh, is this not going to work? Whoops. Let's do this. I'll show it this way. I knew I'd get one of these wrong. Oh. I really blew it. Don't look ahead. This is the one I want. So here's the robot. I wish I could move it up just a little bit. Yeah. Here's the robot interacting with Aaron. It's safe to interact with. It's able to feel forces. He's able to give it objects. It sees him. It reaches out to his hand. He's able to interact with it. Here's another. This is sped up. This was funded by NASA to be an assistant to astronauts. It's tracking him, watching what he's doing, and it's an assistant to make his life easier for simple tasks. Okay, now we'll go back to the. Sorry about that. Now we'll go back to the thing. So, all the pieces for making robots being able to interact with people are sort of there. It's a matter of getting out in the world and doing it. And for that, I want to return to academia versus industry. Not versus, but comparisons. And talk a bit about how to get your research to have direct impact. And this explains why I left MIT and went to Heartland. Here's the way. You've got a good idea in your research. You want to get it out into the real world. What is the classic way people use to do that? They hope. Most common way. And then they complain it isn't happening. So that's why I left MIT, because I had all these ideas about how to make robots more useful to people directly, and I decided I shouldn't sit here and complain that the young whippersnappers aren't out there making it happen. I'll go out and do it myself. By the way, that's complaining it isn't happening is often the same as the latter. You could have a commercial sponsor, but unless you have the sponsor personnel in your lab, it's not going to get transferred out in the real world. You can't just have a sponsor, send them a paper. It's not going to make things happen. You really have to interact with people in the sponsoring organization. And you don't get any financial reward for that, and so some people don't like that. You can consult for a company and try and push your idea on them, or you can go and start a company around your idea. And to really do it, you may have to leave academia. So, to get from a PhD to a commercial system, maybe you've got this brilliant idea, and you can hope other people use it, but then you say, okay, I'm going to do it myself. Well, you soon realize that the brilliant idea you had is only really 10% of the problem. Making it real is another 90%. There's a lot more work. And now you've got a robust demo that you can go and raise funds with. Now the real 90% happens. Now you turn it into a real product. Uh-oh, we got the product. Oh, we haven't manufactured or sold any yet. There's another 90% for manufacturing, marketing, sales, distribution, dealing with returns, service, sustaining engineering, etc. So it takes a lot of other stuff besides the brilliant idea. So the Roomba from iRobot, I had a robot in 1992 in my lab which vacuumed floors. It had a few problems, like it sucked all the dirty air through the computer boards. But we, worked on it for 10 years, and then we got something that was real, and then a further 8 years of refinements until what you buy today. So 18 years of work to get it out into the world. Academia is not industry, and I want to just end by giving a little comparison. I'm not saying one's better than the other. I'm just saying how things are different. Comparison of the reward systems. You get rewarded differently in academia than you get rewarded in the commercial world. In academia, it's all about elegance and novelty of ideas. In the commercial world, it's about something a customer wants to pay for. They're often very different. In academia, if you have a lot of ideas, that's good. Sometimes in industry, you don't want a lot of new ideas. That just gets in the way of really getting stuff out the door. It's the reliability of the product. In academia, you get rewarded for showing your idea or technique has lots of applications. In the commercial world, no one cares about the technique. They just want the thing to work. In academia, the ideas have to interface to a conference paper. That's the critical thing. In the commercial world, they have to interface to the rest of the product. And I'm not saying one's better than the other, just that they're different. And in academia, the idea doesn't have to be practical. In the commercial world, it has to work and it has to be cheap. And that's where the transition comes. And the artifacts that people build in academia it needs to work for the duration of the experiment. In the commercial product, it needs to work for hundreds of thousands of hours. In academia, the sponsor's coming. So there's 6 PhD students buzzing around the robot, until the sponsor gets there, making sure it works perfectly. In the commercial world, the person just bought this thing, and they feel like they paid too much for it anyway, and it better just work when they take it out of the box. They don't want the 6 PhD students coming with it to make it work. As a result, because you've got these PhD students who are infinitely patient, it can have an arbitrarily sucky interface in academia. That's a technical term. It must be easy to use in the commercial world. And it gets polite applause at a conference, even if it's a stupid idea. Very good, very good. No one's going to buy it. And lastly, communications challenge. And I compare here how an academic sees an industry engineer and how a CEO sees an academic. And this first one, for me, as I was CTO of iRobot for a long time, and I didn't get it for a long time. Engineers in industry won't read scientific papers, not because they're bad people, but in general, they don't know how to read papers. And this was a real revelation to me. I'd be at iRobot, and people would say, we've got this real problem. How do we tackle this issue? And I'd go away and I'd think, and I'd come back with half a dozen papers. And I'd say, here, the kernel of the ideas in these papers. And I'd come back 2 weeks later, and I'd say, so what do you think? And they said, what do we think about what? The papers I get. Oh, we didn't look at them. And it's because a bachelor's level student hasn't really been trained in how to read a scientific paper. We use really weird language in academic papers. We hedge. We don't say, this is the best thing since sliced bread, you should use this. In comparison to other methods, this has certain advantages. Is that good or bad? The CEO, on the other hand, trying to work with the academic, CTO, thinks that the academic has contempt for customers. One of my great examples was he was an MIT graduate engineer at iRobot. We got back reports from Iraq that the soldiers didn't like the menu-based interface that we had on our robots there. And one of our engineers said, well, we need smarter users then. Okay, we'll tell the Army to hire different people. What we ended up doing was replacing that menu-based interface with a Game Boy interface. And suddenly we had 85% usability of the robot in less than 5 minutes of experimentation. An engineer doesn't care about everything that academics care about, intellectual debates and academic vindication. Academic cares way too much about their pet technique or approach, says the CEO. An engineer will only implement what they understand, says the academic, because in academia, we tell our graduate students, go figure it out, and we expect them to be able to do it. Engineers in industry can't necessarily do that, so it's a bit of a mismatch. And the CEO, who's working with the academic, says the academic isn't willing to compromise, even if it means shutting down the company. I've got principles. We shouldn't do it that way. An engineer wants hard numeric specs and then wants to engineer to them. The academic out in the industry is always saying, well, you can't really have concrete specs. We just need it to go faster. We need it to be better. And they claim that it can't even be formalized. So the language is hard to cross the boundaries. I'm not saying that one is good or one is bad, just that it's sometimes I think people jump from one area to the other, and we see this with sponsors coming to MIT, not realizing that there are different reward systems and different methods of evaluation, and it sometimes leads to a lot of miscommunication. So I told you today about academia and industry, exponentials, demographics, etc. The pieces are all available. And for those of you who are working in robots, these are the capabilities that I think will make all our robots better. And I'm not going to list them because I'm way over time. So with that, I'll thank you for having me here. And I just want to add that I'm very honored to be giving the Dertouzos lecture because Michael was such a mentor to me. And I'm so glad to have been invited here. Thank you, Victor. Are we taking questions? Questions? Yeah.
How much of your earlier ideas 20 years ago that you wrote in your papers, like the philosophy and also the implementation, still matters in your commercial?
Yeah, the question first one here was how much of my stuff from 20 years ago is still there. In the commercial robots, lots and lots of compromises. Lots of compromises. Some fundamental leaning towards certain approaches, but certainly compromises because there's so much power to be had from other ideas. So I can't quantify it, but we couldn't have been successful without giving up on sacred ideas that became non-sacred. Yeah.
We should wait till we see people actually bring a robot to their house and like start teaching them how to cook or something like
Bring them into the house
and teach them how to cook something.
Or how to cook something. Okay. Well, if you want to clean the floor, I got a deal for you. Cooking. Leslie Cowbling is working on it academically here in terms of getting around a refrigerator. I don't think that we're going to see such robots built for that purpose anytime soon. We're going to see robots built where there's more of an addressable market, making them capable at doing similar sorts of tasks, but in other domains, and then people will start experimenting and bringing them in. So we're not going to see it, I don't think, in cooking in the home, and we're certainly not going to see it I don't think, but other people tend to think this, I don't think we're going to see it in terms of home care robots. I think right now trying to build a robot to give medical care in the home is a pretty tricky thing because who's going to pay for it? Everyone's worried about health costs. No one's going to pay for it. So trying to go after that market right now is not the right idea. In my own case, I decided that manufacturing was something where we really could have an addressable market, and that was a place to put emphasis. And then we'll get out of that technologies which will be useful in those other things, and the business case will make much more sense then. There are other markets, and certainly the military one is as the defense budget comes down, the number one cost in the Defense Department is personnel and injured personnel. So we're going to see much more emphasis, instead of expensive fighters that maintain a human in them, we're going to see much more emphasis on unmanned systems across the whole spectrum, not just from weapons, but logistics and having people drive trucks makes no sense. Having people unload trucks, and Seth Teller's project here is about that. So I think that's, we're going to see these developments in high-value places, and then it will trickle into these other places later, rather than a frontal assault on the home or healthcare. Yeah?
Within the domestic services sector, what do you feel are the most promising applications of, say, humanoid robots or advanced robotics?
Within the domestic? Yeah. I think we already see them in cleaning floor care. We see them in lawn mowing from some companies, sort of routine sort of care. I think bathroom cleaning, sort of things that people don't like doing, folding the laundry. You start to see some YouTube videos of robots doing that sort of thing. It's going to take someone to push them to make them happen, because they're a fairly constrained task, unlike cooking, which is a really under-constrained task. So I think you'll see more and more specialty robots for those sorts of specific, boring tasks that people don't like doing. Cooking has an interesting thing. Cooking gives people an inner reward, that they've done something good for themselves, for their partners, and for their families. So you may not see cooking for that reason for a long time. Yeah?
What do you think it would take to sort of bridge the gap between industry and academia?
Bridge the gap. Well, I didn't say the gap was a bad thing, by the way. I just said there's a difference, and you need to understand that as you jump back and forth between them. There are many places which are starting to have much more industry collaboration at the master's level, say, but the cost of that is you never then do anything truly radical, because industry doesn't want to pay or get involved in anything radical. So there is a place for academia. There is a place for Sylvia McCarley to do crazy, stuff way off in the distance. And I think we need to make sure that we lobby with our funding agencies and our governments and other places to continue to support that, because it's important. So I'm not saying bring them together. I just want to make people understand that there is a difference and what they're signing up for as they move back and forth between them. Yeah?
With the catching and praising and good job and so forth. So how we're training our dog. We have a new dog, not very successful. But one of the things we also do, which always the nice trainers say not to do, but it seems to be the only effective thing, is to punish it. So have you ever thought, is that part of the training? How would that translate to a new robot? Did you think about it?
No. No. Yeah, no, the penalties, yes, but, well, you did see prohibition. You saw Una May there prohibiting the robot and giving the voice. Yeah, well, she was saying...
Yeah, no.
But we weren't training it, no, yes, yeah. But we were able to detect it, certainly, as your dogs are able to detect it. Well, they're able to detect the no, they're just not acting on the no, I suspect.